Okay, here we're going to talk about free body diagrams and Newton's first law, but first we'll review a little bit about forces. If a box is being pulled across a surface by a horizontal rope, the force that's applied by the rope is called tension. The force that resists the motion of the box is called friction. The force of gravitational attraction between the Earth and the box is called weight. And the force applied by the surface that's perpendicular, or rather the force that's perpendicular to the surface on which the object rests, is called the normal force. So the normal force is exerted by the surface on the box, in this case. So free body diagrams and Newton's first law. Newton's laws are all about forces and acceleration of objects, and Newton's second law will get into acceleration and how force affects the acceleration of an object. But since we're dealing with a lot of forces, we need a way to keep track of all those forces, and that's what free body diagrams, or FBDs, are used for. So often an object will have more than one force acting on it, and that can become complicated. So a free body diagram will show all the forces acting on an object. And only the forces acting on the object. So they will not show the forces that the object exerts on other objects. They are only the forces acting on that one single object or mass or free body. So we draw a representation of the object in the center of the diagram, and then we draw the forces acting outwards, and those forces are represented by arrows. We have to remember to label the arrows with the appropriate force, or forces in each case. Here's an example. A ball is falling downward through the air. Draw a free body diagram for the ball. So here's our ball. And we don't have to draw the object. You can just draw a dot to represent the center of the object if you want. In this case, it's not too tough to draw. We have the force of gravity acting downward on the ball. And we have the force of air resistance acting up on the ball. So we can just label that F sub air. How about this one? A book is being pushed rightward across a table. Draw a free body diagram for the book. So here's our book. We have the applied force. We have the friction force acting opposite to the direction of motion of the book. Force of gravity acting downward. And the normal force acting upward, or perpendicular to the table. So we're assuming that the table is horizontal in this case. One of the key reasons that we draw free body diagrams is to help us find the net force acting on the object, or in other words, to find the sum of all the forces, or the total force acting on the object. Sometimes we have to resolve all the vertical and horizontal vectors in order to find the resultant, or that total force. Let's try this one. A book is being pushed across a table with a force of 5 newtons to the right. The force of friction is 2 newtons to the left. The gravitational force is 10 newtons down, and the normal force is 10 newtons up. Find the net force on the book. So we've got our free body diagram here, and you'll notice that all the forces are labeled, and we've also labeled those forces, including magnitudes, which helps us to organize all the information so that we don't miss anything. Now we can determine the total force, or the net force, in the horizontal direction, or the x direction. So we have the applied force plus the friction force, so 5 newtons plus negative 2 newtons, which gives us 3 newtons. Notice that we use negative 2 newtons because friction is opposite to the direction of motion. So we're taking left to be negative here. Vertical forces, we have force of gravity plus normal force. I'm taking down to be negative, so force of gravity is negative. So we get a net force in the vertical direction, or y direction, of 0. So the net force in this case is just 3 newtons to the right. What if we have 0 net force? A weightlifter holds a weight above his head by exerting a force of 1.6 kilonewtons up. The force of gravity acting on the weight is 1.6 kilonewtons down. Draw a free body diagram of the weight. What's the net force on the weight? Here's our free body diagram. So the applied force is 1.6 kilonewtons upward. Force of gravity, or the weight itself, is 1.6 kilonewtons down. So the net force is 0. We add those two values together and we get a total of 0 force. Newton's first law tells us that if there's no net force acting on an object, the object will remain at rest. At least, that's one possibility. The other possibility is that if there's no net force acting on the object will remain in motion with the same constant velocity. So that means that it will keep moving at the same speed with the same direction. Conversely, if an object's at rest or is moving at constant velocity, there must be no net force acting upon it, or the sum of all the forces acting upon the object must be 0. This is called inertia. And it was Galileo that first gave us the idea of inertia. Sometimes inertia helps us, and sometimes not so much. Here's a question. An object is being pushed along at a constant velocity by a force of 5 newtons to the left. What is the force of friction acting on the object? Well, if the velocity is constant, that means that there's no net force. So the force of friction must be equal in magnitude and opposite in direction to the applied force. So the friction force must be 5 newtons to the right. Next, we're going to do a lab inquiry activity in which you're going to build your own accelerometer, and we'll try a few questions for practice.